Hello, I'm Eduardo Martiniano, and this is my final project presentation on recognizing handwritten digits from images using the k-nearest neighbors algorithm, also known as KNN, and implemented entirely from scratch. I will begin by explaining what k-nearest neighbors is and introducing the MNIST dataset. Then I'll walk through how I prepared the dataset, how my KNN implementation works, and the results it achieved. According to IBM, the k-nearest neighbors algorithm is a non-parametric supervised learning classifier that uses proximity to make classifications or predictions about the grouping of an individual data point. And in simpler terms, it is a method of classifying a new point by looking at the labels of its nearest neighbors. While conceptually simple and easy to implement, KNN can still perform surprisingly well on complex classification tasks. The MNIST dataset is a classic benchmark in machine learning. Its name stands for modified NIST because it's a cleaned up version of earlier handwritten digit data collected by the National Institute of Standards and Technology. The dataset contains images of handwritten digits labeled with their numerical values. Those digits are made up of 28 by 28 grayscale pixels, each represented by 1 byte. In MNIST grayscale, 0 stands for perfect background white and 255 stands for perfect foreground black. The first file in my program is mnist.py, which is responsible for loading the dataset with each image stored as a row in a matrix with 784 columns, 1 per pixel, to allow mathematical processing. A key step here is normalizing the grayscale values by dividing them by 255, which scales the pixel intensities to a 0 to 1 range and ensures that no single pixel scales the distance calculations, which noticeably improve the classification accuracy. The file also loads the digit labels, which are the actual digits from 0 to 9, and splits the dataset into training, validation, and test sets. The second file, knn.py, contains the implementation of the k-nearest neighbors algorithm. For each image in the validation set, represented as a point in a high-dimensional space, the function calculates its distance to every other point, each representing an image in the training set, by using a vectorized form of the Euclidean distance, specifically NumPy's linealg.norm method, which significantly improved performance by computing all the distances much faster. After calculating all distances, it selects the k closest samples from the training set and predicts the label by majority vote among those neighbors. Something to point out here is that although the function predictKNN can have access to the ground truth labels from the validation set, it only uses them for live feedback by printing the predicted labels alongside the actual labels for demonstration purposes. And actual classification logic does not rely on those labels in any way. Once the predictions are made, the model evaluates its performance by using a simple accuracy function that compares predicted labels against the actual ones. These are the results from evaluating the model with different values of k ranging from 1 to 10. The accuracy remained consistently high, around 95%. The best performance occurred at a k value of 3, with 95.68% accuracy, and the lowest was at a k value of 2, with 94.48. This is actually a great example of how tuning hyperparameters, and in this case the value of k, can impact the model's performance. But despite the minor variations, the performance still remains strong across all tested values, showing the robustness of this implementation of the k-nearest neighbor algorithm. Here are the references I used for this project. And finally, I would like to thank God for the strength to complete this work, my instructor and advisor, Dr. Perugini, for his guidance, and my family for their continued support. Thank you for listening for my presentation. All the code is available in the GitHub Repository linked in the video's description, and here's my contact information if you have any questions.